So far we have done the design for beams to resist bending moment and shear forces, which is also applicable for footing as well as slab, and the other one we have done that axial loaded column, and now we shall learn how to design for torsion. So, torsion where it is applicable. So far that this lecture concerned, this is our lecture number 27. So, design for torsion, and now let us come that where the torsion is really applicable, that where it acts. If we take a cantilever slab, say we would like to say cantilever slab supported by a beam, a cross section I am drawing. It could be other way also, beam. So, this is your beam, that this beam is supporting this cantilever slab. So, obviously, you will find out that if you take one beam say like this, maybe simply supported also possible. In that case, what will happen? Then you will find out not only the bending moment or forces acting here, you will have that torsion due to this moment. So, that means here you have to design it for torsion also, and this beam you have to design for bending moment, for shear forces, as well as for torsion developed due to this slab. Similarly, it is possible if we draw it in plane. This is a cross section. If we now draw say a beam plan, we are drawing the plan here. So, if we draw, this is plan, please note it is not the elevation. So, what will happen, due to this beam torsion will be developed at this point, because this beam will develop that apply certain kind of torsion like this, and for that also it will design, but that torsion only applicable at this point, or maybe you can say over the width of this beam, whereas in this case this torsion is applicable over the like this over the whole beam from one end to other end. So, this is the, so you can find out that there are so many other cases where it is possible that where torsion will be developed. So, how shall you design that? What we generally do, there we can say that direct, that means when you are talking say bending moment, and the other one shear force. So, we can directly compute the effective depth, that 0.138 FCK B d square equal to say mu as per the limit state design. So, we can find out the depth directly. The mu is the ultimate moment developed due to this bending moment, that your whatever load applied, and shear force also we have that shear force, that is your say V or Vu. So, from there also you can find out the shear stress developed say tau V, and we can find out, so tau V times say Bd equal to say Vu. So, we can find out the shear stress, and critical stress also we can find out. So, tau V minus tau C, from there we can provide the shear reinforcement. But regarding torsion, so regarding torsion we do not go directly. What we do, we find out the equivalent bending moment developed due to torsion say Tu. Tu the torsion applied after say factored 1, that means after multiply with 1.5 or whatever the appropriate factor, and then we can find out the Tu, and this TU, that there is no such scheme or no such formula from where we shall directly get the D, because here we are having that you can say 3 parameters or 3 things are being applied. One is bending moment, another one is shear force, another one is torsion. So what we shall do it here, we shall find out the TU, we shall find out TU, that how it is actually applicable, what is the equivalent one that for bending moment as well as for shear force. And this one we shall find out in clause, for your reference, clause 41, page 74, IS 456 2000. So this is your that clause for limit state of collapse. And that is torsion. Okay. So we shall do this particular one here. So what is our objective then? If I say this is your MU, this is your VU, then we shall find out, which is a function of TU and MU also, that we shall find out ME, that equivalent bending moment, and VE, that equivalent shear force. So which is a function of that you say TU as well as MU, VU, like that. And what we have to do, what we have to provide? We have to provide the reinforcement. So obviously the reinforcement will be here for bending moment, the reinforcement will be here, the longitudinal reinforcement, and for this VE, that you have to provide the shear or wave reinforcement or the stirrups. So these 2 things we have to provide. So what is the idea behind that? If we take it, say any section, say this is your say torsion, then shear stress is developed like this over the surface, which is true for circular one also, for the non-circular one also. So that means shear force, you will find out the shear stresses at different fiber that is developed. So if we can now, the shear stress developed here, so if we can resist the shear stress providing say reinforcement longitudinal, which is coming equivalent to your say bending moment from where we are getting, and the wave reinforcement or stirrups we are providing, so which is your say shear reinforcement, and that we shall do it here. That is the thing, that is the philosophy here, how we are taking care of the torsion. So due to this torsion, how the shear stress is developed here on the surface, and accordingly you have to provide the sufficient reinforcement so that we can resist shear, that cracking can be avoided, and so that longitudinal reinforcement and your wave reinforcement. So what is the that what our code says? This is very simple one, we can say, for equivalent shear force. So I can say in a particular section we can say VE, where that torsion is acting. So VU, the shear force from the usual whatever way you have got it, plus 1.6 TU by B. This one available in clause, just for your reference, clause 41.3.1, page 75, IS 456 2000. So VE equivalent shear VU, that shear that developed due to your say applied load, whatever is coming in the usual way, it will come from the analysis also, that we shall do it in the next few classes. For a total frame we shall do it. TU, torsional moment, and B, breadth of beam. So, here one parameter is in your hand, rather in our hand, that is B. VU and TU, that is coming from the analysis due to applied load say. Now, the equivalent shear, that we can reduce it taking say proper width of the beam. That means, since it is at the bottom denominator. So, what we can do it here denominator. So, we can take that B, say maybe that generally we take it say 250, which is governed by the wall thickness. We can change it to 300 also. So, that means in unusual cases that where we are getting the shear force is quite high, then we can at least we can do some kind of say your changes, reduce it by taking proper B, though it is in a linear parameter, but even then we can change it. So, V, that means there is no such big thing, only thing we have that we have to change the, using this equation let us find out the corresponding equivalent shear force, and then we shall go as per the standard procedure of design of shear. The other one, that is for the equivalent bending moment. So, I can write down so let us write down here ME1 equal to MU plus say MT. This is for the applied load and this is for the torsion. So, MT equal to TU divided by 1 plus D by B by 1.7. So, here MU bending moment at the cross section, and MT, that equivalent that moment, bending moment due to torsion we are getting. D is the overall depth, B breadth, TU torsional moment, now we have one more thing, ME1 equal to MU plus MT, and this is available, that clause for your reference, clause 41.4. To be more specific, I can say 41.4.2, page 75, IS 456/2000. The parameter 1.7 or the parameter 1.6, that obviously because we generally come to this one, finally we come to a say optimum one, so that it is safe. But in actual case, if one is interested, one can go for the whole analysis, one can find out little different. but finally we come to this 1.6, 1.7 for design purpose, so that we can, it is applicable for the wide range of say your rectangular sections or for beams. That is the objective here, that how we generally come to the that your say all the clauses wherever you are having the different parameters. One can say sometimes we find out something say modulus of elasticity say E, that is say 5700 root over FCK. So, if you one is interested for design say or so from the analysis or from the experiment, one can find out the value, maybe it is coming say 5200 or 5300 like that, but finally we are coming to that particular value, so that it is applicable to wide range. That is the basic concept in any design code and for any country. So, if even if we find out that in say American code they may vary little bit, say UK European code it may vary little bit, but almost you can say it is coming towards certain value which is closer to that. Okay. And there is a committee for each and every country also, that for a particular code, say IS 456 there is a committee, similarly for say IS 800 for steel, similarly say IS 875 for each and every code there is a committee who are looking after the things and coming to a point that okay, this value may be quite sufficient for wide range and applicable to our say Indian standard or Indian condition under. Okay. So, now I would also like to tell something more, that here also you can find out that empty that one, the d by b, that means in the earlier case only we have the parameter that b with by which we can manipulate or rather we can reduce the value. Similarly, here also choosing say d by b and then we can find out that empty we can reduce that empty, that also we can do it here. And one more thing I shall tell you, that if we take say span by depth ratio say here say for simplified case say 20, then we shall find out that it will not be with that. If we start, then it may happen that we are really going that your value that one will be very very less. Anyway, so let us find out what more thing we can do it. Let us find out. There is one more thing, that is your say for transverse reinforcement. That is your say shear reinforcement. We find out here say ASV, that your say stirrup, that area of stirrup or reinforcement. It says TU by SV, SV is the spacing of stirrups or web reinforcement, B1 D1 times 0.87 Fy plus VU SV divided by 2.5 D1 times 0.87 Fy. We can find out the area of steel using this formula in clause 41.4.3 page 75 IS 456 2000. What we shall do it here, that ASB we can find out, that means I know TU, I know VU, BU1, what is BU1? Fy we know, say Fe 415, so 415 Newton per square millimeter. So TU is the torsional moment, sorry, VU shear, the it's not the one other than that CTU, not we have not taken equivalent. Please note that VU the shear whatever it is coming due to applied load. SV spacing of stirrups, let us say, because finally we have to provide that one as stirrups. We call it wave reinforcement. So, we have to provide stirrups SV, and this B1 and D1. B1 center to center distance of corner bars in breadth direction, please note. Center to center distance of corner bars in breadth direction. What is that? So, we have B1 and we have D1. If this is your beam, so we are having reinforcement so B1 means there are maybe so many bars. B1 means this is your B1 along breadth direction B1. So, what about D1 along the depth direction? So, B1 will be equal to B if this is your B. So, B minus that clear cover this side 25 millimeter, clear cover this side 25 millimeter, minus that half of the diameter here, half of the diameter. So, that means 1 diameter. So, center to center distance of corner bars in breadth direction. So, let us write down for D1 also. D1 will be equal to similar fashion, center to center distance of corner bars in depth direction. So, overall depth capital D minus that clear cover for beam 25 for usual cases, minus that half of the top bar, half of the bottom bar, and we can find out D1. So, what we can do it then? ASB, that means we know TU, we know B1, D1, FY, everything we know, only thing we do not know SV. Now, what we in usual cases, what we do in general cases, the SV we generally take it, say maybe that say we are stirrup spacing say 200 millimeter say. So, if we assume that okay, we shall provide 200 millimeter as per our that codal provision, which should not be more than certain value, on the basis of that we can choose say 200 millimeter, 250 millimeter, so like that. If we choose it, then we can find out ASB, and now if we know ASB, so let us choose the diameter of bar, and if it is whether it is 2-legged or 3-legged or 4-legged, depending on the situation we shall provide. So, that means for each and every design there is a standard, there is a specific procedure. Here what we shall do, that we shall do it that we provide SB and then we can find out. In other way also we can do it, that means from this equation we can take SB out and we can SB we can take it say 2-legged or 3-legged, on the basis of that also we can find out. Or in other way also we can do it say ASB by SB also we can make it. That means, so the thing is that whether we shall make it say I am telling number 1, choose SV as per the code, that we should not be more than certain value, all those things, and find ASB and provide that bar dia. This may be one case. Second case could be choose bar diameter in other way, that ASV, find SV and provide as per the code. that whether it is coming within the less than that value within the limiting one. The third could be the standard one that we have done it for the beam in the beginning. That means I can take it as ASB by SB also. So ASB by SB also we can find out, and accordingly from this because it is it's not so difficult. So ASB by SB we can take it, we can find out ASB by SB, and then from there we can find out that what should be the corresponding value, either selecting ASB or selecting SB, we can find out that. Okay. So these are the three procedures that whatever way we shall do it. Okay. Now let us start one example, but before that I shall tell you one more thing, that is I have told you in the very beginning that mu1 equal to mu plus mt, that is there, and mt we have calculated here. Now there could be another possibility that mt we have got it, that is greater than mu. The case, first of all, that is that we are adding up that mu plus mt, and where we shall provide that once in the longitudinal reinforcement, that mu in most of the cases mu, which is actually in the bottom the reinforcement we have to provide, that means mu plus mt. Now in another case it is possible that mt is greater than mu. When mt is greater than mu, then we have to provide the reinforcement at the top for, and what is that value, what is the moment, that will be mt minus mu. That mt minus mu that we have to take it, that means it is possible me2 also, that is another case, which is equal to mt minus mu. So mt minus mu, that means say let us say I have told mu1 equal to mu plus mt, where mt equal to tu 1 plus d by b divided by 1.7, and this is one case. The other case is that if mt is greater than mu, then I shall take me2 will be equal to mt minus mu. So this is other case, and for that we have to provide the reinforcement at the top. We shall provide the reinforcement taking me2 equal to mt minus mu. Here also I have seen in this one our code says, and that you will find out, that is in clause 41.4.2.1 page 75 IS 456. Okay. Now, but I have seen in a few other books, at least one book I have seen, and that is where that Professor Dwaratno, ex-professor of IIT Kanpur, he is having one book of that limited design of reinforced concrete structures, where I have seen he prefers that even if it is say not less than say mt and mu, let us do not check that one whether it is greater than or less than, even if it is less than, then let us provide the top reinforcement taking that mt, only mt. So that means here what I would like to say, that in design, even that our code says specifically, even then also there is some kind of say practice also, and obviously that it depends that those things, mainly we are following that Professor Varghese book, but here also you will find out. So there is a difference of opinion also. So anyway, it does not matter that way, but but what we can do actually, after all we are providing that say top reinforcement for the hanging bars. So that also we can check, and we can find out that whether it is sufficient or not, considering that mt value only. That also we can check if it is sufficient, or we can provide at least that value, there is nothing wrong that way, at least, because after all we are providing the top reinforcement that one say for hanging bars, even if we do not require. So that also we can check, but strictly speaking, that as per this clause 41.4.2.1, that we do not need it if mt is less than mu. Okay. So let us start one example problem. Let us take simply supported beam, span 5 meter, live load 25 kilonewton per meter, torsion 25 kilonewton meter, please note 25 kilonewton meter from end to end. That means all along the beam this torsional moment is acting. Concrete M20, steel Fe415. So, data given FCK 20 Newton per square millimeter, Fy 415 Newton per square millimeter, L effective span, say here we can take it say 5 meter, live load or WLL say live load 25 kilonewton per meter, T unfactored, that not the design one, T given as 25 kilonewton meter. Let us calculate the load. So, step 2 say load calculation. We shall try say few trials, okay, because instead of directly going to the value, it is worth that going say all the calculation, because what are the process, how do we repeat the whole calculation. Let us start like that, because I do not want to make the final value and see that as if it is a magic we have got it, but it is not like that. When you are designing, then we do lot of say your repeating steps. Okay. So, let us say assume width of the beam 250 millimeter. If we take a span by depth, let us take a span by depth. Say let us take say 20, because for simply supported beam. So, what about the depth then? (5,000) by 20, which is coming as 250. If we start using this value, then you will find out that it will be very less, this value. So, let us start at least say, because that is why I do not want to go that computation, because if we start say I have to calculate the self load, sorry, self weight of the beam, and then you say live load given, then I have to calculate that mu, that bending moment due to that applied load, and then I have to find out that equivalent bending moment due to torsion. So, let us, because if I start with 250 millimeter, then it will be very less. So, let us take for calculation of the self weight the overall depth, let us take say 500 millimeter, okay, because from 250 to 500 to going to that level, obviously it is better to, you can try checking with that value, at least you try with 250 and check that how it is coming instead of directly going to that 500. Okay. So, self weight .25 is the width times 0.5 is the overall depth times 25 kilonewton per meter cube, which gives us 3.125 kilonewton per meter. Design load (1.5) times 3.125 self weight, approximately you can say 300 kg per square meter. That means in few cases what we can do, instead of going directly, we can take say 400 kg per square meter also we can take it, or 4 kilometer per square meter. In that case also sometimes we take it that way also. So 1.5 3.125 plus 25, that is the live load, and which comes as 42.1875 kilonewton per meter. What about the bending moment? mu equal to w u say ultimate times L square by 8. So 42.1875 times 5 square divided by 8 equal to 131.83594 kilonewton meter. We can take it at say 131.84 kilonewton meter. Few designer prefers say okay, we shall go, since it is coming in the calculator, so as much as possible we can go. The other alternative also we can take it say as say simple, say up to 2 decimal, that also we can do it. What I am trying to say, that when we design it, sometimes it happens that you have to submit the design also, design report also, that how we have come. Not only that, our final objective though to make the drawings which will go to the site, but at the same time sometimes for proof checking or for other purpose, for record also, we have to submit the design also. Now in that case it happens that we can go to this as much as possible, but there we can take in the very beginning, we can write that whether we are gone up to say 2 decimal or 3 decimal, because after all that after that it will only unnecessarily, it will take time, but we can round up to that say 2 decimal for when you are talking say kilonewton meter. So similarly for meter, we can go up to say only say after meter we can go say maybe say 2 or 3 decimal, because up to millimeter we can go. If it is say millimeter, then we can go only 1 decimal, if it is, or we can keep it in millimeter only. So those things we can write down in the very beginning of your say design note, that okay, these are the things you have followed. Now what about the torsion? That is equal to 1.5 times 25, so 37.5 kilonewton meter. So we can find out the equivalent. Equivalent moment due to torsion. So okay, equal to TU 1 plus D by B divided by 1.7 equal to 37.5 times 1 plus D we have taken 500, B we have taken 250. You can take it 0.5, 0.25 also, but after all we are taking this on millimeter, so cancelled here, and 1.7, which comes as, let us see, 37.5 plus 3 by, multiplied by 3 by 1.7. What I mean to say that, let us see that what is the factor. I can get it directly, I can get the whole value, but that I am not interested. I am interested in usual cases. It may happen that sometimes it happens that you are checking that what should be the TU times how much. So that, let us say that means here we can get it as a 37.5 into 1.7647, that means 76% extra, that means 1.76. That's what I am interested to know, because only from this one you will not get that idea, you will not conceive that what should be the value. That means here if it is 37.5, in worst case I can take it as a just simply I can multiply with 2 also, the twice of that. So what I mean to say that in that way those values factors are coming. So I can say that 37.5 into 1.7647 and which is equal to 66.176 equal to say 66.18 kilonewton meter. So I can find out 66.18 kilonewton meter. This one thing I would like to make it here comment, that generally it happens these values, that whether you can for any design purpose, if you have to feel it in a sense that whenever you are getting any numerical value, that numerical value whether it is coming all right or not, that you have to check at each and every step. When you are doing the design, that each and every step you have to check that whether that value is coming all right or not. Because if you do at least few, maybe say 4 or 5 problems like this, then you will have an idea that okay, that value at any step, if you find out any unusual value, then immediately you can find out, you can understand okay, there is something wrong. So that's why these few steps that your each and every step you have to do it, and accordingly you can find out. That means say whether you are doing any calculation mistake or not. So just simply putting all those value in your calculator, you can find out this value, and that what we do it. But since we are getting this idea that twice or something, that it should not be more than twice or something like that, what is the range? So immediately we can find out whether we are getting that value correct or not. That is the standard procedure of design that you have to do. Okay. So what about the equivalent bending moment? Equal to 131.84, that is the AMU, we have got it due to the applied load, plus equivalent moment which is coming as 66.18 and which is coming as 198.02 kilonewton meter. Okay. So what about the effective depth? We can compute, we can check effective depth. Let us compute effective depth. So we have the same formula. So 0.138 FCK BD square equal to mu. Let us write down here ME. This is our ME. So mu means here, as per our that say due to torsion, so we should apply here ME. So we can find out D equal to 198.02 into 10 to the power 6 divided by 0.138 times 20 times 250 equals 535.71 millimeter. Overall depth D equal to 535.71 plus 25 is the clear cover, plus let us take that bar diameter little higher side 25 by 2, that is 25 millimeter dia bar, let us assume. So we are taking a little higher side, maybe 20 millimeter may be sufficient. So which is coming as 573.21 millimeter. So we can provide overall depth, say 575 millimeter. we have come to a problem. The problem is that we have taken the self weight as a 500 millimeter, breadth width of the beam that is 250 millimeter, 573.21 millimeter, that is the overall depth to be provided. So, just we are really in a marginal situation, 575 millimeter. So, that means we do not know that due to the self weight, we do not know whether that we shall still will be in the safer side, because that 535.71. Another one, we have taken that your say TU, we have taken here TU, that D by B. So, D is that say your say 575, that means due to this torsion also that your bending moment will change. So, if we really provide that one, say one alternative could be that we can go say 600 millimeter and we can check all of them, we can do it. Instead of that, what we can do it? We can do it other way. Let us try this way, that we shall change the width. Okay. So, let us change the width. So, assume width of beam say 300 millimeter, overall depth 575 millimeter. Here overall depth 575 millimeter. Since I have changed the 300, I could reduce it. Or anyway, let us do not change it, because it may happen that that value will come less. Okay, but anyway, let us do not reduce it at this stage. So, TU 1 plus D by B by 1.7 equal to 37.5, 1 plus 575 by 300 divided by 1.7 equal to 64.33 kilonewton meter. Self weight equal to 0.3 width of the beam times 0.575 overall depth of the beam times 25 kilonewton per meter cube comes as 4.3125 kilonewton per meter. Design load equal to 1.5 times 4.3125 plus 25 equals 43.96875 kilonewton per meter. So, you have got the design load, we can calculate that MU equal to 43.96875 times 5 square by 8 equals 137.40234 kilonewton meter. Let us say 137.40 kilonewton meter. So, we have got MU. So, equivalent bending moment equal to 137.40 plus 64.33 equals 201.73 kilonewton meter. D equal to, let us calculate D. So, let us you see that 493 millimeter only. Overall depth (493.59) plus 25. Let us still take 25 millimeter dia bar we shall provide. So, 531.09 millimeter provide overall depth. D equal to say 550 millimeter. 540 also we can provide, but anyway let us check for 550 millimeter. So, we can now we can change that value, because self weight also, that means if we provide at 550, that means here. So, we can provide that self weight. Let us check the self weight again. So, 0.3 times 0.55, 550 times 25 comes as 4.125 kilonewton per meter. Design load equal to 1.5 times 4.125 plus 25 equals 43.6875 kilonewton per meter. mu equal to 43.6875 times 5 square divided by 8 equals 136.52 kilonewton meter. Equivalent moment so 37.5, 1 plus 550 by 300 by 1.7 equals 62.5 kilonewton meter. So, this is due to torsion only. This is due to torsion only. So, equivalent bending moment equal to 136.52 plus 62.5 equals 199.02 kilonewton meter. So, that means finally we can set to this value that 300 by 550 millimeter, and then we can take it 199.02 kilonewton meter or the bending moment, and we can provide the reinforcement for this bending moment. Okay? I think we shall stop it here. We shall continue in the next class.